Good day, everyone. Today I'm going to speak with you about conformers and isomers. Okay, so the first thing we're going to get into, jump right in, is some of these Newman projections that you see here. And then I'm going to show you a molecular model kit representation of what I have here on the board, because two dimensions doesn't really tell you an awful lot about what's going on here. So this is 2,3-dibromo butane. And ignoring the configurations, in other words, where these things are bonded, we're just mainly concerned with what kind of space each particular coordinate takes up, and you know, how things are rearranged. Okay, so when you look at a Newman projection, you see in the front that there's this sort of junction, okay, like a three-tine junction. Okay, that's going to be the carbon that's going to be in the front that you're going to be looking at, okay? And then to the back, this circle here is going to represent that carbon that's behind it. So if you were to look at what you're seeing, let's say, with what's over here, this is what is referred to as an eclipse conformer. So that means everything is basically covering one another. These CH3 groups are covering this CH3 group, this bromine group is covering this bromine group, this hydrogen is covering this hydrogen. Okay, now how you would look at it, imagine these red balls that you see right here as being bromo groups. Okay, so look at how clustered and congested everything is, all right? If you look at it from the side, you can't really see too much, but if you're actually looking at it like sort of down the barrel of a gun or something, it's you can see that everything kind of overlaps completely or eclipses. Okay, so this is going to be the highest possible energy you can have for this particular compound. So it would need some kind of extraordinary amount of energy required to fit it in this particular position. The reason why is that things sort of like people that are claustrophobic. You know, they need some space. They need some room to relax. Right? They don't want someone up in their face. So, in other words, what nature is going to do is going to allow it to sort of relax a little bit and turn. Okay, so this is what referred to as gauche, or just to the left, right? So I just turn one thing to the left here a little bit, and you see now that things are not overlapping quite as much as they were on that left or the beginning conformer that I was showing you. Now look at where carbons 2 and carbons 3, again, junction, circle, okay? I'll just point that out here. Those are essentially where the rotation is taking place, right? So if I'm just going to flip it upside down and show you here how it's twisting and twisting and twisting, that's just to indicate that there is no bond breakage. There's merely just bond rotation about a sigma bond, right? All right, so let's take everything to its maximum to where nothing is really going to eclipse or overlap or anything like that, and that would be anti. Okay, so this anti conformation that you see here is simply what you're going to be looking at like so. So you're going to see something diametrically posed on the other end, right? So this is carbon 2 in the front, carbon 3 in the back. Okay, and you see also how these bulky methyl groups, this isn't a really fair representation of bromo. Bromo is going to be much larger. It's probably going to be about the size of, I don't know, maybe slightly smaller than a tennis ball, but it's going to be big. So when you have it up like that eclipse, it's really going to bump uglies, and it's not going to play nice. You know, the two aren't going to play nice with each other. So what you really want to have is a completely anti configuration like what you see right here. That's going to be the lowest possible energy. And I implore you to pick up a set of molecular model kit if you haven't already. And, you know, just kind of work with these because they'll be, as you'll see very soon, is going to be very helpful in your training. Okay, so right now how I have it is in the ball filling model, or sorry, space filling model. So in other words, instead of ball and stick like you'll see later, you have these little pegs that are kind of double-ended and they're very small and they have like a little wrench that they include in the kit where you can pry them out. But what they do instead of using the stick is to get everything kind of into its largest sort of form, closest to the next nucleus that it's bound to. Okay. Okay, so now we're going to jump into cyclic alkanes and their conformers. Now, I've drawn everything in 2 dimensions here, so I'm just kind of give you a basic rundown on how each of these particular species is in terms of what Vesper or electron repulsion kind of drives them to be spatially, and how they're laid out. Okay, so the first one we're going to go over here is cyclohexane. So cyclohexane, if you read ahead, is very much stable. So it's going to conform to what is referred to as a chair conformation. And I know that looks very beautiful, but bear with me here. It kind of looks like a warped up lightning rod a little bit, at least per my take. So there's going to be a total of 6 points, right? But these are all going to be configured in a way to where you can let those hydrogens that are branching off of here, right? Doesn't have any substituents about it, kind of breathe in terms of where they are, right? So we've already seen previously that if you have any type of overlap or if you have other sort of substituents that are nearby that are kind of bumping into one another, things are going to be higher energy. Okay, so the lowest possible conformation for cyclohexane is going to be in this chair position. Now there's a boat and then a twist boat. Those are going to be higher energy conformations when they are going and reverting over. So this is going to have to undergo or overcome some kind of energy barrier to twist and kind of look at its mirror image. Now, you'll see that once things become substituted, it'll be a little bit harder for you to overcome that particular barrier. So as it is, you know, things can kind of waver back and forth and kind of go between these different sort of conformations, but to go and default to this chair conformation like you see here. Okay, so these bond angles are going to be at about perfectly 111 degrees, which is even more relaxed than you can think of for typical tetrahedral complexes. So remember, this is all sp3 throughout. Okay, so all these sp3 hybridized carbons are going to perfectly situate everything at 111 degrees. So things are going to have great space to kind of breathe, and this carbon to carbon and carbon angle, if you will, is going to be very ordered. Okay, so you can almost think of it like lawn chairs, right? Everything can kind of stack neatly up and below, very uniformly. And if you were to build 2 of these with your modeling kit, particularly with the ball and stick way, you can definitely see how things can conform, and you see very nicely structured LDF between those. Okay, so So this actually freezes at a fairly slightly higher temperature than actually water does. So it'll freeze, I think, at like 6 degrees C, maybe 4, somewhere in that neighborhood. Can't think of it off the bat, but nonetheless, you see a very ordered system there. So when I say it's the golden standard, it's really one of the most robust or strong rings out of all the assortment that you see here. Now, this isn't to say that it's more robust than, say, a benzene ring, but in terms of cyclic alkanes, this is really kind of the golden standard. Okay. Now, when we're talking about heat of combustion and how much energy is required to combust and break down these cyclic alkane rings, it's usually compared to every single one of these on average, right? So per average, if you're looking at that table on 4.1 on page 175, you can see that this is going to be the highest energy in order to break down. Okay. It says higher heat of combustion per CH2 unit, more unstable the ring structure. So you're going to see the highest really over here, where the cyclopropane is, where the angles are actually going to be much more strained at 60 degrees. Okay. And this is going to be predictably at 90 degrees, sort of like a right triangle. Okay, so cyclopentane can kind of waver going between, we'll say 102 and 106 degrees. So it's slightly more kinked than you would think of for typically 109.5 for all of your tetrahedral geometries. Okay, so you can think of it like an open envelope. So one CH2 group is always going to be sort of poking out of the actual plane of the rest of what you have here. Now, back to cyclohexane for a minute. You'll also see that things are going to go up, down, up, down, up, down, right? So that's to make sure that everything's in its proper space and that there's no, overlap or bumping into, hydrogens that are hanging off or other carbons, etc. Now, you could also take a look at some of the Newman projections that your text has here to kind of give you a better idea for why certain, CC bonds are going to be a little bit more eclipsed than others. Now, cyclobutane, right here at the bottom, this is going to be a little bit more puckered, right? Because you have 2 carbons that are going to go down, 2 going up at all times. So it's going to lessen that torsional strain. So essentially you're going to see, it says 88 degrees C, somewhere in the neighborhood, right? But by, things going up a little bit and these going down a little bit, these 2 CH2 groups going up, these going in, it's not going to be flat like how you would imagine. Okay. Again, the reason being is because those CH2 groups have to not eclipse in any way. Okay, and then cyclopropane is going to be the most extreme. Okay, so it's going to be easiest to kind of pop open. Reason being is it has no choice. There's always going to be some hydrogen either sticking out. I'm going to do some dash wedge. Okay, so each one of these hydrogens that are going into the plane of the board are going to be eclipsing, just like all these on the outside are going to be eclipsing. So it's going to be a highly strained ring system, and also that 60-degree bond angle really doesn't help, okay, in terms of stability. Now, cycloheptane, drawn kind of ugly way, 7-membered ring, so 1, 2, 3, 4, 5, 6, 7. Okay, it just doesn't have the same order like how you see for cyclohexane. There's going to be a little bit more of malleability in terms of where things kind of zigzag, right? So it's not going to be perfect in an even number fashion like how you see here. There's always going to be some sort of warping, if you will. So you can also take a look at that on table 4.1 and see where those CH2 thermodynamic data fall. All right, so here's just a naked cyclohexane ring. Okay, so this is going to be in the chair position. And of course, exactly like how I drew, there is this sort of zigzag up, down, up, down. They call it head, tail motif in your text for how things are positioned, okay? Now, when you do it, when the chair flip occurs, you're going to get this sort of boat conformation, okay? Now, notice what you see up at the top here, okay? So a boat, sort of like a canoe, right? So these two carbons are going to be pointing up, sort of puckered out from this sort of 4 carbon base that you see right here. And these hydrogens are going to be kind of bumping into one another in terms of where they are. So that's going to be an issue. All right. So then there's also the twist boat, right, where that's going to be slightly higher in energy. Again, because you're actually getting other hydrogens near one another by doing so. Okay. So that's sort of the twist boat conformation that your book depicts. And then back on over to where it's up, down, in the stable chair configuration. Okay. Now, we're going to look at monosubstituted, so we're going to pluck off one of these hydrogens here. Then we're going to put a big old bulky methyl group on the side. Okay, so hopefully this camera should get it all. All right, and we have something that's hanging off in what is referred to as equatorial. So, if this were the globe, you would consider this, right there around the equator, right? But when you do a chair flip, what's going to happen? Whoop-de-whoop-de-whoop. Now it's going to be axial, so it's on the North Pole, so to speak, right now. Right? So when it's axial like this, it's going to be bumping into these other hydrogens, so that's kind of a no-no, right? We want things to be in a relaxed or more ordered, environment. So in other words, this is going to really favor the methyl group being in the equatorial position, right? So it's not encumbering any sort of space above the ring, right? Where things are kind of a little bit closer in terms of distance. Okay. Now we're going to take another example here. We're going to strip off another hydrogen. We're going to add a an amine here to make a di-substituted cyclohexane ring. Okay, so things are pretty happy and content right here. As you can see, both things are equatorial. So when you flip this up, so this is a 1-3 relationship, so just so you know. So the 1-3 relationship, things are practically bumping into one another, right? We've gone from equatorial to axial here. So in other words, really driving home message here is that if both things are axial, then or even maybe one substituent is going to be axial, it's not going to be very stable. Okay. Now, this is what is referred to as a cis configuration, so not a conformation configuration. So don't get the two mixed up. It's not potato potato. It's, you know, they're two different. Configuration is going to be bond related. Conformation is going to be rotation related. Okay, and steric related. So when I say sterics, that means, you know, bulky things that are bumping into one another essentially. Okay, so this is going to be high energy. You want things to be down into the lower conformation. See, even I'm screwing that up from time to time, to where things are going to be more ordered and less susceptible to bumping into one another. Okay, now let's go with a trans configuration. And 1-2. Okay, so both are equatorial right now. Still kind of looks like a cluster mess. I'll keep it PG here. Okay, so, but when you do that chair flip, what happens? Or sorry, this is what things are going to look like trans in a 1-2 relationship. So notice how that methyl group is sticking up at the top. This amino group is sticking off at the bottom. But when we do the chair flip, boom. Okay, so they're right next to one another. And yeah, that's not going to be, it's going to be higher energy as a result. So things might be a little bit more comfy in the axial positions. Okay. But it's also, they're also kind of bumping into some of the hydrogens that are up above and below, which are also axial. So play around with this a little bit. Look at some of the differences between 1-2, 1-4, 1-1, or sorry, 1-1, you know, 1-3. And you can see some of the major kind of distinctions when you're doing the chair flip. See what they look like and see what how they're drawn. Okay, now moving on into connectivity and configurations. So let's say you have a computer and you're not entirely happy with it, right? You think that you can get better streaming quality, you can get better processing, yada, 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 right? And would you get it conform to how you would do it, or would you configure it in a way to where you can maximize things? You would configure, right? You would kind of change things up and maybe put things in different orders to get them to be to your optimal sort of standard of quality that you're looking for, right? So some people customize and get their own computers made as opposed to just buying something stock that's already sort of conformed to one type of application, right? So if somebody is really looking into high processing and gaming, they're going to get something that's configured and has a cooling tower and blah, 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 blah. Okay, so with molecules, that's really no different, right? You want to have, if there's a particular drug target or something you want to make that's, let's say if you're trying to do a natural products synthesis and you're trying to make a particular type of vitamin or something like that, it's kind of hard to come by, or some kind of natural product that's therapeutic, you have sort of a target goal and you want a particular type of configuration. So it's going to be bond related. Okay. So let's think of just some simple examples here. Okay, so we're looking at cyclopentadiene and let's see, 1, 2, 3, 4, 5. So pent 2-ine. Okay. So these are different molecules entirely in terms of how they look, right? So but are they constitutional isomers? And when I say constitutional, I mean, do they have the same molecular formulae? Well, let's see. Okay, so with the previous exercise that I had for you guys, where I was looking for you to count all the sigma and pi bonds, is somewhat related, right? So draw out all the hydrogens, and let's see if we come up with the same count of each. So 1, 2, 3, 4, 5, 6 hydrogens. Okay, and then 5 carbons. So C5H6. We have 5 carbons here. We're not going to argue that. Okay, but how many hydrogens? We have 3 here, 2 here, and another 3 here. So that's going to be a total of 8. Okay. So in other words, we have 2 additional hydrogens on the right for this particular compound. So these are not isomers of one another. These are not constitutional isomers of one another because they have a difference in counts of hydrogens. So in other words, this is slightly more saturated than this ring that you see here. This is the same count of carbons versus a higher count of hydrogens for the molecule on the right. Okay, so let's take a look at another example here. Let's look at this T-butane versus N-butane. Okay, so 4 for carbon, can't argue with that, right? But this is going to be branched, so remember that you're going to have, let's say, 1 hydrogen hanging off there in the middle, so 3, 6, 9 hydrogens plus a 10th hydrogen right there, so C4H10. Okay, and then we have 3 on the each end here, so that's a total of 6 plus 1, 2, 3, 4 for a total of 10 on the inside for those methylene carbons. So in other words, C4H10. These are constitutional isomers. Okay, so these are not. Okay, how about another example here? So we have benzene. So it's just going to be C6H6. Okay, and then we have a cyclopentadiene that has a methylene group or a geminal alkene hanging off of that. Okay, so if we're going to count our hydrogens, it's going to be 1, 2, 3, 4, nothing here, 5, 6, and we have a total of 6 carbons. So in other words, this is going to be C6H6 as well. So these are also going to be constitutional isomers of one another. Okay. All right, you can try some of those others. It's a little bit more difficult, a little bit more bookkeeping with some oxygen thrown into the mix. But one thing I want to get you guys to sort of identify when you're looking at particular structures like this is seeing what kind of unsaturation you have. So notice how I had C6H5 here, C5H8 here. So I had the same count of carbons, but I had more hydrogens on the right side as opposed to the left. Okay, so each one of these double bonds that you see appears is going to be one hydrogen deficiency. Okay, now there's going to be one hydrogen deficiency here, another hydrogen deficiency to make it 2, and then a ring is actually going to be a third, because if you could imagine, if you were looking at a linear counterpart, you'd have to tear one of these bonds and then add another 2 hydrogens, one on each side, to fill that octet on those particular carbons. Okay, so so you would not see the same or if they were to split them apart and add those two hydrogens, you would see the same amount of hydrogens, carbons, so therefore those would be constitutional isomers. Okay, so index of hydrogen deficiency, or IHD. Okay, so it's going to be one double bond, or one pi bond, okay, or half a triple bond, okay, or one ring. Okay. All right, so with that said, there are no indexes of hydrogen deficiency here. Indices of hydrogen deficiency. What? Okay, how about how many there are here? You have 1, 2, 3, and then a ring, so that makes 4. And then on this particular structure, you have 1 for the ring, 2, 3, 4. So that's a total of 4 as well. Again, so if the molecular formulae are in agreement with one another, then that means they're by default they're going to have the same hydrogen deficiency. There's just going to be, again, difference in connectivity. Okay, so we're going to look at hydrogen deficiency by the numbers. When I say that, I'm just saying if you were to be given a particular molecular formula, let's say if you were to get some elemental analysis report on what your compound might be, you could better kind of assess what that constitutes, and then you would look at things, let's say with spectroscopy, which we'll get into later in the semester, and you could figure out what that connectivity is. But you kind of need to know what you're working with first before you can make that determination. Okay, so let's see some practice examples here. So we have C6H6 before. Okay, so we're not going to sort of postulate what this could actually be because we have no way of knowing, right? This is just a formula, right? There's no indication of connectivity. We could say, oh, it's probably benzene, but we don't know that for sure. So what we're going to do is plug in our IHD calculation, which IHD, again, index of hydrogen deficiency, is going to be equal to 2 times our carbon, which is going to be 6, plus 2 plus N, which is going to be 0. Okay. Minus H, so we have 6 hydrogens here. Okay. And we don't have any halo groups, so that X is just going to represent a singly bound halide. That's also going to be struck out. Okay. So now we have 12 plus 2, which is going to be 14, minus 6 is going to give you 8. So 8 divided by 2 is going to give you 4. Okay, so that would certainly align with benzene like we saw in the previous example when I was trying to compare constitutional isomers, as well as that funky looking pentagon with a geminal alkene hanging off of it. Okay, so it's benzene's a constitutional isomer. Okay, let's go with another one here. So this is CH2O, which will give you very limited options in terms of what that might be, because carbon is the only thing that can bond to 3 other things. Everything else, you can just form a duet with hydrogen. You can only form 2 bonds stably with oxygen. So it's really going to give you a limited selection, but we still need to do the IHD here. So 2 times 1 plus 2, okay, and then minus 2 from the 2 hydrogens here, and this is all going to be over 2. Okay, so 2 plus 2 minus 2 is going to give you 2. over 2 is going to give you 1. Right? So that is going to be formaldehyde. Okay? Now let's really go for the Olympic gold here and do capsaicin. So if you're a fan of spicy food, this is what you're ingesting. Okay, so we have C18H27NO3. Plugging that into IHD here for your calculation. That's going to be 2 times 18 plus 2 plus n, which is going to be 1 here, minus 27. Okay, so you're always going to look to have an even number in the end, just FYI. And then it's going to be over 2. So oxygen doesn't factor in, and there are no halides. So in other words, plugging all this stuff in, you're going to have, let's see here, 2 times 18 is going to be 36. 36 plus 2 is 38. Minus 26, 38 minus 26 is going to be 12? Yes, 12. 12 divided by 2 is going to give you a total of 6. Okay. Well, that would make sense because capsaicin is going to look something like this. Hopefully you'll be able to see it. I think I can just erase this. I think you guys are probably confident with that answer. At least I hope you are. Okay, so capsaicin. Again, that's the molecular formula. It's going to have a hydroxyl group hanging off of it. It's going to be a phenyl ring. And then there's going to be an ether, a methyl ether there. Okay, so you're going to have 1, 2. So that's going to be an amide. So 4 IHD here, 1 from this double bond, that CO double bond. Okay, and then whoop, whoop. Okay, and then another double bond to round it out, and you have a trans alkene over there, the further to the right. So 4 here, 1 here, 1 here for a total of 6. Okay, so now we're going to determine the IHD by site. So in other words, we're looking at a compound, trying to deduce relative count of unsaturation here. So first things first, let's start with the one on the left here. We have 2 rings, so there's 2 right there. Okay, and then we have 3 double bonds, so we have a CC double bond here, and then a CO double bond, so that's going to be a total of 5 IHD. Okay, next one up, we have 1, 2, 3 double bonds, then another cycle to make it 4. Okay, and then the last one here. Okay, so we have 4 right off the bat with the phenyl ring. So it's 4 from the phenyl ring. A cyano group is going to be CN triple bond. So, you know, even if I have things shorthanded here, you're still going to have to kind of visualize what this may be. So this is going to actually look like is going to be CN, right? So carbon's going to be singly bound to that phenyl ring junction, and you're going to have 1, 2 pi bonds. So in other words, that's going to be an IHD of 2 for that particular moiety, right? Or portion of the molecule, functional group, whatever. Okay, and then CHO, so that's going to be what is referred to as an aldehyde, right? So in other words, okay, so there's 1 there. So in total, it was going to be 1, 4 to be 5, 6, 7. Do not count sigma bonds. Recall that anything that's a pi bond or a ring is going to add into your IHD. So that IHD for this particular compound is going to be 7. Lucky number 7. All right. Hope that was informative. Next chapter is going to be, or chapter 5 is going to delve into more, I guess, interesting stereochemistry and isomerization. So please be sure to read ahead before you look into that next module video. And again, be sure to check in for office hours, and we can go over some more examples here if you have some other questions about other examples within the text, or just some general questions that you might have sparked in your mind watching this. All right, thanks. Have a great day, everyone. Bye.